Okay, let's do it. So this average with respect to n of the velocity of the electrons, I defined it like this, is the summation from I equal to 1 to n of ui, where ui is the velocity of the ith electron. Then the graph of this thing, the average of u versus time, is like this. So it goes and accelerates due to the acceleration a, which is due to the field. So it does it for some time, but then it collides and then it completely loses all the memory that it had. So just consider a bunch of electrons. While they are moving, they are being accelerated, but when they collide, they are now suddenly going in all random directions. So their average velocity, that will be 0. So it starts with 0, then it uh, goes for some time with acceleration a, and then it collides and then comes back to 0, and it keeps happening. And the average time for which uh, this going up happens, that will be 2 times capital T. So this capital T is the average with respect to n, so I have defined it over there. Okay, so this capital T is the summation from I equal to 1 to n of Ti upon n, where Ti is the time required for the ith electron to collide starting from any point in time. So you have a lot of electrons. Some of them will collide really fast, right? They will take no time and they will just collide. So we're just talking about some particular point in time. From that point, how much time do we need till when the electron will collide? So some electrons, they will collide really fast, some will take a lot of time before they collide. So we are talking about only one collision right now. So basically, if you graph this u for a lot of electrons and then you try to match it, right, then it would look something like this. So graph this ui versus small t graphs. So graph all of them and then take their average, right, superimpose them and then divide them by n. That will give you a graph looking something like this. Okay. In some books, they take this complete thing, so the total time required for it to once again collide and go down, that is capital T, right? They take it in some books. I'm going to take that as 2 times capital T. So in my work over here, capital T is this thing, right? So I've defined it like this, and yeah, that creates a lot of confusion sometimes. At least I had this confusion. So you should know that there are 2 definitions of capital T, and this is the one that I'm using. Okay, a is the uniform acceleration on each electron due to the field E. So from that we can write a equal to E times small e. So E is the charge on the electron with the sign upon the mass m. Okay, then the drift velocity ud, so this is a vector quantity. We can write it like this. Cool. So this is very obvious, because this red line that gives us the average velocity, which is the drift velocity. So it's the average of the average, basically. Okay, next we are defining some new stuff. So J, which is known as the current density, it's a vector quantity. It is how much current flows per unit area through an imaginary surface that is perpendicular to the drift velocity. So over here, if these electrons have a drift velocity in this direction, we will just imagine that there's a surface, and then we will find out the current through that surface and divide that thing by this area. So I've done exactly the same thing over there. So this capital D, it's the density of the electrons in that metal. By density, I mean the number of electrons per unit volume. So if that's kind of a constant thing, because there are a lot of electrons, so it's approximately constant. So that number we are using over there. So E is the charge, you know that. So this density times the volume. Volume is just capital A times ud, drift velocity times dt. So ud dt, it's this length, that times capital A, that will give us this volume that I've shaded, that times the density, that gives the number of electrons that are in this volume, and that times the E thing, that will give us the charge. that upon dt. Okay. uh, so we have J is a vector collinear with UD. That's nice because yeah, so J is a vector as I told you, and it is by definition collinear with this drift velocity. And from this equation you can directly see the relation that J is EdUd. Okay, J is a property of the electrons inside the boxed volume, while current is the property of a given surface area. So current in this derivation is a scalar, and current is the property of this A thing, this surface area. So right now this surface area is just imaginary, so we don't talk about the current right now. But if the surface area was not imaginary, if this was a real surface like in this graph, in this diagram, then we would talk about the current. And current is basically how much charge goes through that surface per unit time. I think that's well known. Okay, so since we know that J is just EdUd, and we also know what UD is, right? So UD is this thing. We can just substitute that into here and get this thing. So this E squared capital T upon M, this is a constant which is dependent on the material that we are using and the temperature and other stuff. So I'll just call this as sigma. So sigma is the conductivity. It's called conductivity. So J is sigma E. Cool. Then you have this thing. So here we're just considering an elemental volume. So elemental, I don't know what I should call it. So it's just two surfaces which are a very small distance dx apart, and you have electrons with drift velocity ut inside them, and you also have the field which is like this. Okay, and these are going, yeah, whatever. So the diagram gives everything, right? So dV, which is the difference in the potentials of these two surfaces, that is E dot dx. That's also well known. So the current across the real surface of area vector. Okay, so this A is, it's area vector, it's not just the area. So A, the current across A is E into capital D into capital A dot dx. So dot, because yeah, the volume of this green thing, right, the volume of the electrons, yeah, that will just be capital A times dx, right, because it's a prism basically, a slanted prism, yes, but it is a prism. So that volume times the density, once again, that times the charge, that gives the total charge that went through the surface, and that upon dt. So dt is the time required for this yellow layer to go through the whole thing and get to that blue thing, blue surface area. Okay, where dt is the time required for the green volume of electrons to completely pass through, which means the time required for the last electrons to reach the surface. Okay, also notice that this angle is theta, so we can say that dx, which is this length, this vector length, is ud into dt cos theta, right? That makes sense. So this this orange layer or yellow layer, this has to go all the way, so this point, it has to go all the way till here, right? So it has to travel this much of distance in time dt, so that would mean this much of distance is ud dt, and then multiply by cosine theta, so you get this component. Okay, where was we, where were we, right? Dx equal to ud dt cosine theta, so that means a dot dx. So basically dx is just the projection of this ud dt. It's the projection, horizontal projection basically, right? So it's the projection along this area vector A. So from that we can say a dot dx is a dot ud dt. Okay, so from that I is E capital D times a dot ud dt. So just substituting this equation into that upon dt. So rewriting, we can write it like this: a dot E capital D ud. Now we already know that E capital D ut, uh, where was this? Yes, E capital D ut, that is our J. So we can write I equal to capital A dot J, and we also know that this capital J thing is sigma E. So I is A dot sigma E. So rewriting it's sigma A dot E. Okay. Next, this potential difference, it's E dot dx. So its magnitude, it would be like E dx cosine theta, right? The dot product, yes. And I, its magnitude would be sigma AE cosine theta. So just divide these two equations and you get this equation finally. dv equal to 1 upon sigma dx upon A times capital I. So 1 upon sigma, I will just write this as rho, the resistivity. So you have dv equal to rho dx upon AI, and then if you integrate this, you get this equation. So it's a non-vector equation. That's why I just wrote this dx upon A like that, and no components or anything crazy. It's just a non-vector equation. So notice that you always need this A to be perpendicular to our dx. That's the way that we are defining A everywhere, right? So like at least for this surface, so if you are already defined the surface, then you can define dx in a way that it would be perpendicular. That makes sense, right? Okay, where was I? So integrating this, we just get delta v equal to the integral from x naught, so some value of x till x naught plus L and all this stuff. So if this inside stuff is this, if this integrand rho a upon, okay, rho upon A into I, if this thing is constant, then we can write delta v equal to rho L upon A times capital I. So it's going from x naught to x naught plus L. That's why this L over there. Cool. So from that, so once again, writing this rho L upon A as another constant, we can write delta V equal to capital R capital I. So capital R is the resistance. Cool. So here's all the renaming of quantities that we have done. Small e squared capital D upon m, that is sigma, which is the conductivity. 1 upon sigma is the resistivity. Then the resistivity times length upon area, that's the resistance. This formula is also well known. And 1 upon the resistance is the conductance. So basically this is the formula for resistance, the complete formula, which would be capital R equal to small m upon E square capital D. So all of this stuff is dependent on the material, and length upon area, that's dependent on the dimensions of the material that you're choosing. So this is an intrinsic property and this is an extrinsic property. So resistance depends on both, while resistivity doesn't, because this part is the resistivity. Okay, so yeah, that's it. That is Ohm's law, because finally we got this relation delta V equal to Ri. So for uniform stuff, so uniform density, uniform resistivity, uniform area, uniform current, we will have this equation. So that was nice. Yeah, and this is the more general equation. So that's it. I will see you in the next video.